Good morning, everyone. Today we are here to discuss about the chemistry topics. My name is Advertisement, engineering undergrad from IT branch section A. So my topic name is polymer solubility and its molecular weight, and I unveiling its secrets today. So the first topic is understanding polymer solubility, and I give its a unique name that dance of dissolution. Understanding polymer is the most competitive things today I ever face because it contains so many things like dissolution, molecular forces, etc. So first of all is like dissolve likes. As we know, like always attract likes. The similarly, it patterns also follows in the polymer chemistry. That's polar polymers dissolve in polar solvents and non-polars in non-polar. Second one is intermolecular forces. Intermolecular forces like hydrogen bonding, van der Waals forces, dipole-dipole interactions are can give the crucial roles. Stronger interactions if they have stronger interaction between polymer and solvent molecules, which promotes solubility. Third one is temperature. Generally, temperature uh, give the most impactful reason for this, because if we increase the temperature, solubility increases, which helps for faster dissolution. The next one is solubility parameters and polymer classifications. There are 3 to 4 polymers classification. The first one is Hansen solubility parameters, which is also known as HSP. HSP quantify material solubility by breaking down cohesive energy. As we know that cohesive energy is the most incorporated energy, because it requires polars as well as non-polar bonds to create or dissolute them. The second one is amorphous polymers. These polymers have disordered molecular arrangements, lack defined melting temperature. Their solubility is generally higher because solvent molecules can more easily penetrate the loose structure. They have loose structure, and that's why they can penetrate easily. And this creates its disrupting molecules. So that's why it also called as glass transition or TG element. Third one is crystalline. As we know that crystalline polymers are the highly rigorous, requiring significant energy to breaking down tight. They are tight picking, so they are also the hardest one. Then now study we have the experimental methods for polymer solubility. Solubility can also check by some experimental measures by which was performed only in the lab. First, turbidity. This method assesses the cloudness, polymer, etc. Then the second is viscosity analysis. Viscosity, we take the viscosity of that polymer liquid and check it through the expansion, solvent affinity, etc. Third one is cloud point determination. The cloud point determination is the temperature at which molecular solution begins to turn cloudy, and this will only provides a thermodynamic data. It's not rigorously used because it's only provides a heat related data, not the other things. That means spectroscopy techniques. Today nowadays we can also use the UV, NMR, IR radiations to check the inside polymer solvents, to also check their solubility mechanisms. Then now the how molecular weight shapes polymers, because molecular weight is the most important factor. Chain length and viscosity. First is chain length and viscosity. Higher molecular weight means long polymer chain, because if the molecular weight increases, its chain length increases, and leading to increase in entanglement and higher solution viscosity. So its viscosity also increases obviously. Mechanical powers. Polymers mechanical properties. Polymers with greater molecular weight often exhibit a enhanced strength, toughness, and resistance to deformation due to the more extensive chain interaction. Fourth one is processing challenges. While beneficial for properties, every high molecular weight can make processing more difficult, requiring higher temperature or pressures. Interplay and impact. Connecting solubility and molecular weight. If we increase the molecular weight, longer polymer chains have more sites for intermolecular interaction, making them less prone to dissolve in the given solvent. If we increase molecular weight, it becomes more hard to dissolve that much things to increasing and giving it solvent. Then reduce solubility. If we reduce the solubility, higher molecular weight polymers requires more energy to separate their chains. If the molecular weight was higher, the chain is also becoming so large, and that's why it's incorporated solvent. When we identify or promote in the incorporated solvent molecules, it's also decreases, and hence the solubility decreases. Critical balance. Achieving the desired solubility for specific application also involve the precise control over the polymers. Third, and then now we are moving forward about its application and innovations. Harnessing polymer properties. Harnessing polymer properties means how the polymers nowadays changing, and it's included in our day-to-day lives. Understanding solubility and molecular weight is critical for design polymers with tailored products, because nowadays technology increases, and that's why polymer also came in our day-to-day lives. We are not just only using polymers in agriculture industry, but our medicals material science also used it. There are 2 or 3 uses I will tell you. First is biomedical, that nowadays drug releases systems and biodegradable implants uses polymers. Then material sciences, higher strength composites plus smart plastics and flexible electronics. And now you also know that environmental they obviously use these to upgrade their filtration membranes, etc. And this is the end of today's project or activity, that I totally agree with all the points I mentioned in the PPT, and hope you will enjoy the slides and my explanation. Thank you.